The Confluence project actually is in that space. They're the ones who, well, they did a series of Lewis and Clark commemorations along the Columbia River, and they specifically managed the construction of the land bridge here in Vancouver. So they're leasing that space, and they've actually designed a new exhibit in the main lobby. So you are able to go in there Monday through Fridays to look at that. And it kind of talks about the history of that. Normal hours here. It's their hours. So if they go like on field trips or something, you know, they might be closed, but generally they're there Monday through Friday about 9. Yeah. And if you were here a couple weeks ago, that was part of the spruce mill. It was the only surviving structure from the spruce mill. It was the finance office for the spruce mill. And then it became the headquarters building for the 321st Observation Squad. And more recently, it was the headquarters of the Tears of Joy Puppet Theater in the 1990s. And Charles, if it's okay, I think I'm going to move your computer on top of that stand. Just keep the cables down. just ask everybody, how's the temperature in here? Good. You okay? Okay. Couldn't we all?
Ice cream.
Little biscotti.
I was gonna say scone, but Scotty do better.
Yeah, I can tell.
Nobody's been to the moon for about 30 years. Where's with the mining?
No
I don't
humans.
know, we're gonna find out. There's a gentleman right there that
Costs about $1 million to get, a few gallons of water up there.
this ought to be interesting.
Sure, I'm serious.
I've been reading over the last few years that there's some kind of fuel up there, helium-3 or something. I don't know what form it, how you mine it or anything. I'm just wondering if you picked up on what the essence of this.
Private industry probably first one to look at it. It's profit up there. She's saying,
Ain't nobody gonna get what's with the moon in these United Nations. China was trying, there's gotta be all kinds of treaties before anybody does anything serious there. Pollutes that place. I've been reading some really great stuff about the moon. Haven't read. I mean, I have a lot of cosmology stuff in my personal library. I recently came onto something. She belongs to several things. Church.
Yeah, no, it's a good viewpoint.
They've been monitoring it with 5 big electronic devices, great radio facility, for the last 20 years. They've been monitoring a lot of crazy stuff. I was there with him.
So there'll be a series of archaeology lectures this coming summer.
I don't know if they're pulling one together or not. It's going to be a smaller field scope. So I haven't heard for sure.
I like that series.
Me too. We've had one going for 13 years. So I hope you'll be able to pull a few. You just reminded me, I'll bug the archaeologist about, hey, are we going to do that? At least a bit tired. Sit down for a minute. What class are you teaching? Well, I'm not, I'm not teaching. you're all set there. I told her to contact me directly. You know, it didn't come very positive within a couple weeks, so. Well, see you Saturday. What time does the meeting start on Saturday? 1 or 2? 2. Okay. Yeah, I'll mention it.
Well, I don't want to pay a lot of taxes before they get the technology, because they get the technology.
And by all means, you can. Anybody who's
Right now.
no, it's on. So there's a switch on there. So when after I'm done introducing you, you should be in business.
I'll try and post an update. Thanks for letting me know. There is a link. Where do you see the link? Yeah. Okay. Yeah. Okay. Well, it's on Google. It's on Google Plus. Um, if you go to Hangouts on the Air, you should find it. But if the link's broken, that's a problem. Um, yeah. Which LinkedIn group are you looking at? On my personal profile? Yeah. Hi, Ravi. Yes. Yes. So which group on LinkedIn are you looking at? Or yeah. Yeah, I'm not sure how to fix that at this point. Um, I can't get into LinkedIn right now. No. I'm sorry. It'll be on YouTube. I'll send you the YouTube link. I don't think we can do it live, so I'll have to. Sorry about that. Sorry.
I think it's 6:30.
Okay.
You feel ready?
Yeah.
Go ahead and get things started.
Yeah. Thanks.
Okay. Good evening. My name is Bob Cromwell. I'm the manager here at Pearson Air Museum. It's my pleasure to welcome you here to the third in our series of aviation lecture topics, aviation science, technology, and education. The overall theme of the lecture series is Imaginings of Flight, the Past, Present, and Future of Aviation. And tonight's topic certainly touches on all three, probably the past, present, and hopefully future of aviation. This is the first in what I hope will become an annual event here at Pearson Air Museum to highlight aviation topics to the visiting public. If you haven't been to the museum in a while, I recognize a lot of faces from the last couple nights, but there appear to be a few new ones. If you haven't been here for a while, I hope you enjoyed the reinvigorated exhibits in the main hangar space. And I wanted to make sure you all knew. The museum is very happy to announce, the National Park Service is happy to announce, that we have purchased a very rare 1918 DH-4 Liberty biplane, the only American-built aircraft to fly with American crews into combat in the First World War. There's only about a dozen of these left around the world, and we are having one restored professionally by Century Aviation in Wenatchee, Washington. I just was contacted by them, and they have all but completed the entire tail assembly, they're happy to note. And I'm expecting a progress report from them in the next couple weeks, and I will be posting some images on our website, Facebook site, and hopefully we'll have some other exhibits on the floor talking about progress on that project. If all goes well, that airplane will arrive here sometime in the fall of 2016. It will be restored in the colors of the 321st Observation Squadron as DH-4s appeared here in the 1920s here at Pearson Field. So, with that, I also wanted to specifically thank our partner in this aviation lecture series, the Oregon L5 Society. I will let Charles Radley, who's also the president of the Oregon L5, talk a little more about the Oregon L5 Society and what they're about. If you are interested in it, they did put flyers around the room. And to let you know, they have their monthly meetings here at Pearson Air Museum. And in fact, their next one is this Saturday at 2 o'clock. If anybody's interested, by all means, pop on by. Tonight's speaker, Charles Radley, has quite a long history in space exploration fields. He has a bachelor's degree in physics and a master's degree in systems engineering. He worked for British Aerospace and also moved to the United States in the late 80s and went to work for Hughes Aircraft and worked on various space probe projects. I can let him tell you more about those specific things. And he was a contractor for NASA as well, more recently in the 1990s. Currently, he's a software tester for a healthcare company here in Portland. But we're very honored to have him here. And with that, I will let him speak on mining the moon with a lunar elevator.
So I'm Charles Radley, president of Oregon L5. A couple of people have asked what L5 means, so I'll mention that briefly. The Oregon L5 Society is a chapter of the National Space Society. In the early 1970s, a gentleman called Professor Gerald O'Neill wrote a book called The High Frontier, in which he described how the moon could be used as a resource for mining building materials and construction materials, and the material will be thrown off into space and to build large habitats and solar power satellites. And he decided to make use of what are called Lagrange liberation points. The L stands for Lagrange. In the Earth-Moon system, so the moon orbits the Earth. And if you're really close to the moon, you're in orbit around the moon. And if you're close to the Earth, you're in orbit around the Earth. But there is a fuzzy zone. There's a region where you're kind of orbiting both bodies at the same time. But there's only 5 places where you can physically put an object and it'll more or less stay there. And they're called Lagrange liberation points after a French mathematician called Lagrange who calculated them sometime in the 19th century. And L1 is in between the Earth and the moon, where the gravities balance out. It's 50,000 kilometers from the moon and about 200,000 miles from the Earth. L2 is about the same distance behind the moon. L3 is the other side of the moon, other side of the Earth for the moon, opposite the moon. And then you've got what they call Trojan points, L4 and L5, that orbit the Earth 60 degrees ahead of the moon and 60 degrees behind the moon. And L4 and L5 are the most stable of those locations. And O'Neill figured that's the best place to put large cities in space. And the group, a lot of people thought that was a good idea, and they created what's called the L5 Society. And the L5 Society had various chapters around the country and around the world. The chapter was started in Oregon. Oregon L5 was started, I think, in 1979 or thereabouts. And then in 1986, the L5 Society merged with the National Space Institute, which was started by Werner von Braun, and the new organization was called National Space Society. So the national organization has stopped using the name L5, but the local chapters still use it. Some of them do. And I was elected president of Oregon L5 2 years ago. The previous guy did it for 19 years and wanted to take a break. And I was the last one left standing. So I've been very interested in the moon. I'm part of the Apollo generation. I grew up watching astronauts walking on the moon on live TV. It was just one of the most amazing things I've ever seen. Excuse me. We're kind of disappointed that it all came to an end in 1972. But I was very inspired by the O'Neill L5 idea. I still am. And as time progresses, we get smarter and we learn new things, and there are new ideas. So O'Neill himself died in the 1990s. But since then, we've gained a lot of knowledge, which I think is making the idea become closer and closer. So let me go through some of my slides. I have this PowerPoint slideshow. I'm not going to talk so much about the O'Neill vision as such. I've been trying to find more short-term commercial opportunities. And I've been thinking, what is the commercial value of the moon? You're thinking as a capitalist, I guess. Actually, politically, I'm not really a capitalist, but I understand that the governments are not going to pay for sending humans in space anymore on any large scale. So where people are going to go, it's going to be for commercial reasons. And there's actually quite a lot of money out in the world. I mean, I'll disclose that my father worked for an oil company, and I grew up seeing the scale of what can be done. And if there's a commercial value, there are commercial interests that will pour billions or trillions of dollars into it. I mean, if you look at one oil company, ExxonMobil, their annual budget is about $130 billion a year, which is 15 times the NASA budget. So, if ExxonMobil wanted to go to the moon, they can afford to do it. No problem. The NASA money is chicken feed compared with what's available in the private sector. So let's see what might be interesting. Well, lunar rocks and soil itself actually has value. And believe it or not, there actually are commercial samples of lunar material that exist that have come down in the form of meteorites. I mean, the samples that were collected by Apollo are government property, and you cannot buy them. NASA holds them in a laboratory in Houston. But bits of the moon fall down to Earth all the time, and there is a thriving trade in meteorites. I think somebody mentioned helium-3. Helium-3 is a very unusual isotope of helium. It's extremely rare on Earth to the point of being almost non-existent. And in fact, helium-3 doesn't really exist in nature on Earth at all, except in very, very tiny trace amounts in natural gas. But large quantities of helium-3 were produced in the in the Cold War as a decay of nuclear warheads. It's a byproduct of tritium decay. And when people started making lots of tritium for thermonuclear warheads, they started finding this helium-3 stuff started appearing. And it turned out to have some very interesting industrial applications. It's a very unique substance. And you can do some things like extremely sensitive Geiger counters that can't be, they outperform anything else available. And it's currently selling for about $2,000 a liter, or about $1 million per ounce. And the market right now is worth about $100 million that you can find on the moon platinum group metals. So not just platinum, but the other metals in that group of periodic table. I forget the name of them, like rhodium, rubidium, and a couple of others. They're there on the moon. Then rare earth elements found in, there's a unique material on the moon called creep, which was discovered in the Apollo samples. I'll talk about that a little bit. And since Apollo, a lot of people, the moon does not get much publicity, and many of you may not realize that there's actually a lot of research been going on the moon ever since Apollo. I mean, Apollo had a blaze of publicity with the astronauts, and then there was a quiet spell when nobody sent anything to the moon. The Russians landed on lunar 24 on the moon in 1976. Then nothing went to the moon for about 15 years, nearly 20. And then a whole bunch of probes started going out there. NASA sent Lunar Prospector. Then there was the Chinese sent 2 probes, Chang'e 1 and Chang'e 2. The Japanese sent a probe called Kageyuga. The European Space Agency sent a probe called SMART. NASA sent another probe called Lunar Reconnaissance Orbiter. All of these probes were very, very high tech, with very advanced instruments on them, much, much better than anything the Apollo astronauts had available. So we now have what I call a treasure trove of new data. We know a lot more about the moon than the Apollo days. The samples that were brought back from NASA by the Apollo astronauts underwent a lot of study, and they're still being studied today. Plus, there were 3 samples brought back by the Russians, the Soviets, from some unmanned probes. And the Soviets made those samples available for international study as well. So there's actually been a lot of sharing of samples. Scientists from all over the world have been studying these samples. And the results of these studies were compiled in a fascinating book called the Lunar Source Book, which is actually available online now. It's published by the Lunar Planetary Institute, which is a NASA-funded institute in Houston. And this is about a 400-page document. And I've been reading through this, so this is a great source of information about what the moon's made of and what's distributed. But even this source book came out before all the new orbiters. So there's quite a lot of data to look at. I thought I'd mention rare earth elements. There are several of them, and this is what they're used for. I probably can't even read much of this, but they're used mostly in electronics of various kinds. Your cell phone and your laptop contain most of these elements. And right now, most of them come from China. They're very difficult to find, but our entire electronics industry and even defense industry is heavily dependent on these exotic materials because they have some unique properties. And they're commercially very valuable, and the prices are rising. They're called strategic minerals, and the United States stockpiles a lot of strategic minerals because a lot of them are not available in the United States. In fact, for rare earth elements, here's the global production of how they come from, and 95% of them come from the People's Republic of China. 2% of them come from India, Russia has 2% of them, Brazil 0.5%, Malaysia 0.3%. America, United States has a little bit, but not a whole lot. So there's a security problem. China dominates the market, and they are artificially bringing the prices and making it very expensive. And China's just charging the world whatever they feel like charging because they can. And the prices keep going up. Another problem with rare earth elements, by the way, is when you mine them, there's a lot of toxic waste, especially radioactive waste, because they tend to be mixed in with thorium and even uranium. So there's a huge radioactive waste disposal problem, which makes it, in the US, it's very difficult to get environmental permits to start these mines. But in China, that's not so much of a problem. So they must have a terrible toxic waste problem there with all these green mines. One example is lanthanum, for example. That's one of the rare earths. And semantic curve that shows how the price of lanthanum has been going up over the last 10 or 15 years. This stuff is in great demand and is really going up in price. Probably a good investment. Demand for, I call them REEs, rare earth elements, is growing. China has reduced re-exports. Prices of REEs are rising rapidly. World defense production relies entirely on China. REEs are available on the moon in lunar creep deposits, mapped from orbit by thorium emissions. And I've already gone over this. Why are heavy rare earth elements important? They're used in mobile phones, hybrid automobiles, renewable energy, windmills, that kind of thing. So here is a map of the moon made by the NASA Lunar Reconnaissance Orbiter around 1998. And this shows where these creep deposits are. And you'll notice on the left, that's the near side of the moon, and on the right is the far side of the moon. And you can detect the presence of creep. The creep stands for K is potassium, Re is for rare earth, and P is for phosphorus. Creep is a material that does not exist on Earth. It was discovered in Apollo samples, the Apollo lunar samples, and they found this creep stuff. And it's concentrated in an area known as the Mare Prosolarum Basin, which is this sort of colorful area at the top left. And you'll notice there are four bright white spots where the intensity of the thorium is quite high, and that indicates quite concentrated deposits of creep. I believe what's happening there is the creep actually, this area, this colorful area, was a sea of magma lava at one time. There was an asteroid blasted into the moon, melted a whole area of the moon, and there was literally a sea of liquid magma. And as it cooled down, these creep chemicals floated near the top, and other stuff sank to the bottom. Some stuff was a little lighter. So most of this creep seems to be in a layer about a few hundred meters below the surface. And these four white spots are where meteorites have impacted the moon and exposed this underground creep in high concentration. I've mentioned that we have lunar meteorites that when asteroids and meteors hit the moon, they knock fragments off, and a lot of the fragments escape the moon and they end up entering the Earth's atmosphere. One such fragment was found in the Republic of Oman in the Middle East, and it was called SAU-169, and that has a higher concentration of creep than any of the Apollo samples. This is a picture of the meteorite. You see the two gentlemen who discovered it, and that little dark rock is that meteorite that came from the moon. And it actually traveled from the moon to the Earth 30,000 years ago and entered the Earth's atmosphere and has been sitting there in the desert of Oman until these two gentlemen from the University of Bern in Switzerland discovered it. And there's a photo of it to the right. We know that it came from one of the white spots is this crater Lalande, and you'll see on the sort of top left there's like a little chip been knocked out of the wall of the crater, and that's where that SAU-69 meteorite came from. I don't know how they figured that out, but they figured that out, and there's some very long-winded papers that describe how they figured that out. But it validates the data from Lunar Prospector. The Lunar Prospector orbiters showed that there was a very high creep concentration there, and we actually have a piece of it. So we know it's there. This is a table from the Lunar Source Book that shows the concentrations of the various rare earth elements in creep. Creep is a column on the right. Chondrites on the left are just a regular type of meteorite. And I added those numbers up because I've been trying to figure out whether that's viable to mine it. And so I came up with a number of 0.25% of the total creep composition. of the total recomposition within the creep. And I see data that says projects being considered for commercial development today are from 0.2 to 12% TREO, which is total rare earth oxide. I don't have rare earth oxide numbers for creep, but assume it'll bump it to 0.25 up to about 0.3%. So it's, it's within the kind of commercial threshold of terrestrial mining today. Now, yeah, I'm not really comparing apples with apples, I'm aware of that, but that's just a sanity check. So it could be a mineable ore. The moon is also rich in asteroidal material. Asteroids, lumps of rock that orbit the sun, some of them come close to the Earth, most of them are between planets Mars and Jupiter. Some of them are very rich in platinum group metals. Apollo samples have 1 to 4% impact pulverized meteoritic content in the regolith. The regolith is just a fancy word for soil. The top level of dust on the moon, they call it regolith. Some of the meteorite material is ferrous metal containing platinum group metals. Much higher concentration of asteroidal material probably exists in magnetic anomalies. There's a lot of magnetic anomalies on the moon, which some of them were discovered by Apollo, and we're finding more of them all the time. Ferrous metal is very easy to separate from the silicon dust using magnets. I played around with some numbers on the concentration of platinum group metals in meteorites. And there's some concentration numbers there, which are comparable to the sort of concentrations you get in commercial mines on the Earth. Here's a paper I found in Science magazine, which talks about how the lunar magnetic anomalies are probably results of asteroid impacts. So the previous map I showed of the creep was from the American NASA Lunar Prospector probe. This is the map from the Japanese Kaguya orbiter, from the magnetometer, and this shows the magnetic field of the moon. I mean, a lot of us were taught in high school that the moon does not have a magnetic field. Well, no, exactly. It doesn't have a strong magnetic field like the Earth, but there's still quite a bit of residual magnetism on the moon, and it's been mapped. You see on the near side, on the left, far side, on the right, and you'll see on the lower part on the far side a lot of red and yellow areas. That's the rim of a feature known as the South Pole Aitken Basin, and the north rim of that. That was a huge impact crater, and that's got some of the strongest anomalies. So I theorize that there may be some rich platinum group metal deposits there. Here's an example, of that area. Here you see, just an optical camera image, and what you get is magnetic swirls. You'll see that area. You see all those sort of white, cloudy areas. There's quite a lot of them on the moon. This is the area of the north rim of the Aitken Basin, which I highlighted on the previous slide. What happens is solar wind particles come in from the sun, and they're charged particles, so they get deflected by magnetic fields. And so we know there are magnetic fields here on the moon because the areas of the moon that are bombarded by the solar wind, there are areas where iron oxide is converted to iron by the solar wind. And so they tend to be darker. And the areas which have not been exposed to the solar wind, those tend to be lighter. So you can see the lighter areas here are where there's strong magnetism, which is deflecting the solar wind away from it. Here's another close-up of another magnetic area called the Rhina-Gamma feature. And this was photographed by the Japanese Kaguya probe, which is also called Sicilian. JAXA, JAXA stands for Japanese Aerospace Exploration Agency. I don't know how you say that in Japanese, but that's the English they had a the probe they put around the moon weighed several tons. It was a big probe and had a lot of very sophisticated instruments on it, including an extremely high resolution camera. Helium-3. Okay, there has been some talk of using helium-3 for nuclear fusion. And nuclear fusion reactors with helium-3 have been demonstrated experimentally, but they only put out a little bit of energy. Currently, and they're a long way from being commercially viable, but there are industrial uses for helium-3 today. And in fact, there's a critical shortage of helium-3 today because the United States and Soviet Union were selling helium-3 on the spot market because to them it was a waste product. It was a byproduct of the nuclear warheads that were venting this gas off. And various people discovered that you could do some very interesting things with helium-3, and there are now quite a lot of commercial products on the market which have this gas in it, including hospital MRI machines, Geiger counters. And a couple of things happened in the early 21st century. After the 9/11 attacks, the Department of Homeland Security was formed. Part of their charter was to search for illegal smuggling of fissile nuclear material. So they have a program to put neutron detectors at every airport, seaport, and shipping terminal in the U.S. Other countries are doing this too, to scan every container of cargo to see if it's got neutrons coming out of it, because that's the best way of detecting nuclear material. And the best Geiger counters for this need helium-3, and so demand for helium-3 started to skyrocket partly from the Department of Homeland Security, also from the medical industry. Also, the oil and gas industry use it when in a technology called well logging. And I don't know the details of it, but there's something about you put a radioactive source down into a borehole, and you put down a Geiger counter, and somehow you can figure out how much natural gas is down there. So they've been buying a lot of Geiger counters with helium-3. So at the same time, the demand for helium-3 has been skyrocketing. The supply has been falling off because after at the end of the Cold War and the strategic arms treaties, a lot of warheads have been dismantled. And so there is much less tritium around now than there was during the Cold War. So the United States stockpile is dwindling. And in 2008, there was a train wreck. The Department of Energy announced that they were not going to be able to satisfy the demand, and that the stockpile would run out in about 10 years. So there's now rationing. In 2008, they introduced rationing, and the price of helium-3 increased by a factor of 10 overnight, and it's been going up ever since. These are a couple of government reports from the General Accounting Office. That one's from the Congressional Research Service. And they're interesting reports. I've read them. They talk about this whole helium-3 market. And the helium-3 is abundant on the moon. There is some criticism of why the Department of Energy didn't give enough advance warning. And partly of it was for security reasons. The precise quantity of the helium-3 stockpile was classified until about 2008. Because if you know the amount of helium-3 in the stockpile, you can actually get a pretty good idea of how many nuclear warheads are sitting in U.S. silos. And the U.S. didn't want that information being public. But that information was declassified in 2008, and then they suddenly realized the helium-3 was disappearing. And this is, and then there are some alternatives to helium-3. There are some other types of material like boron-60, but they're nowhere near as good. Helium-3 is rare on Earth and abundant on the moon. one of the best maps of helium-3 we have is from the Chinese Chang'e-1 orbiter spacecraft. That shows on the left the near side of the moon, on the right the far side, south is at the top. Those dark browny areas tend to be the lunar mare, or the low flatlands. They tend to correspond to areas of a mineral called ilmenite. These areas on the moon are rich in the mineral ilmenite, which happens to absorb helium-3 very well. And some of the richest samples of helium-3 actually came from the Apollo 11 landing site, and Neil Armstrong took up a shovel full of lunar dust and put it in a box, and it turned out to have an exceptionally high concentration of helium-3 in it. How do you get, somebody asked how you get it. There's a jump. The University of Wisconsin has been doing a lot of work on mining volatiles from the moon, which contain helium-3. One member of this team, by the way, is Dr. Harrison Schmitt, who is the last scientist to walk on the moon on Apollo 17. He's still actively engaged in this, and he's written books about how to use helium-3 from the moon. Again, these guys are interested in using it for a nuclear fusion fuel, but you can use the same mining technology. You don't need to wait that long. We can do it today because there's a market today for helium-3. And they designed a lunar volatiles miner. There's sort of a little picture of it off to the left, a machine that would travel around the moon, and basically if you take lunar soil and you heat it in the silver concentrator to about, we say 300 Kelvin, it starts to emit gases, and the gases you get listed here, you get hydrogen, you get water, you get a little bit of nitrogen, carbon monoxide, methane, carbon dioxide, and helium-4. And now the helium-4 has 1 part per 3,000 of helium-3 mixed in it. And so you need isotope separation to get that out. And then he says here you get clean fusion energy on Earth. Well, maybe one day, but today we can sell it to other customers. Another useful feature of lunar material is because the Earth weighs 83 times what the moon does. And due to the rocket equation, that means you need hundreds of times more propellant to get off the moon than you do to get off the Earth. And there's an orbit around the Earth called geosynchronous orbit, which is where a satellite takes 24 hours to orbit the Earth so it stays constantly in one spot in the sky. And that's where most of our TV broadcasts and communication satellites are sitting. And it's quite expensive to get hardware out to that orbit. But if you take, for example, an upper stage called the IUS, these numbers here that I went through, for example, if most of the weight of a rocket stage is the oxygen in the oxidizer, it's about 80%. And we can actually get oxygen from the moon. It's fairly easy to produce it. And if we could deliver lunar oxidizer propellant to low Earth orbit, it would reduce the cost of boosting payloads into geosynchronous orbit by a factor of about 7.5. So that's a known market. Okay, so let's talk a little bit about the lunar elevator. The moon orbits the Earth, and the moon is at a distance here, you can see, of 385,000 kilometers, isn't it, 250,000 miles. And there's one of the Lagrange point number 1 sits between the Earth and the moon, and it's about 55,000 kilometers from the moon's surface. And there's some folks that have done some studies on this. One of the first was by Jerome Pearson, who had a NASA contract for NASA Institute of Advanced Concepts in 1979. And he calculated that this was was doable. You can actually put a piece of tether, and you'd have the center of mass of the system sitting at Lagrange point 1. So that's stationary with respect to the moon. It's not stationary with respect to the Earth, but that's okay. And you can have a station at the L1 point and reel down, 55,000 kilometers worth of cable down towards the moon, and then away from the moon you need a counterweight, and that can vary, but in this configuration it would be a cable of a distance of 195,000 kilometers. Now that sounds pretty big, but the good news is that the gravity of the moon is pretty weak, and there are commercial materials today that are perfectly capable of carrying that kind of load. And I have some at home, and I forgot to bring it with me. There's a sample. There are 4 or 5 materials. Here is talking about Xylon and Dyneema. Xylon is a material that's made by the Toyota company in Japan, and it has the highest. It has a very high strength to weight ratio, much stronger than Kevlar, for example. Dyneema is a very similar material that's made in the Netherlands. Either of these materials could be used to make a lunar elevator. There's also a material in the US called M5, but in the US, the US government has a monopoly on all supplies of that material, so it's not commercially available. And with a lunar elevator, the cost of a soft landing on the moon, I'm not going to say it's free, but it's about a factor of 6 lower than using chemical rockets. And the cost of, all you have to do is launch a spacecraft from Earth, and the expensive part of the Apollo landing mission was the lunar module, landing the lunar module down and bringing it back up again. You can put a rocket launching from Earth can put 6 times as much payload weight to the Lagrange point than it can soft land onto the surface of the moon. Okay, so space travel costs are measured in dollars per kilogram. So this lunar elevator represents a saving of about 6 times dollars per kilogram for soft landing on the moon, because once you've got your payload at the Lagrange point, and with a lunar elevator in place, the cost of soft landing on the moon is basically 0. And the cost of collecting material from the surface of the moon and delivering it to the Earth is basically 0. Whereas using chemical rockets, those are quite expensive things to do. So, and then again, once you've got lunar oxygen, the cost of transferring from a close-in low Earth orbit to L1, that will drop dramatically too. So the cost saving starts to become more than a factor of 6. I said the cost previously, saving of about 7.5. If we go to geosynchronous orbit to the L1, it would be about 5. So you got 5 times 6. So we're talking cost saving of about 30 times. So mining the moon begins to look like it might become cost effective. Here's another picture of an example. I'm trying to give it some sense of scale. Jerome Pearson, when he wrote his paper in 1979, had a design of a lunar elevator that weighed about 3,000 tons. But that was way overkill. We don't need that. I've been involved with a group called Liftboard Group, and we've been trying to run some numbers for a minimalist lunar elevator. And we came up with one design which would weigh about 30 tons. So even though this cable is over 200,000 kilometers in length, it's very, very lightweight. And fiber only needs to be 0.2 millimeters in diameter. And 0.2 millimeters in diameter over a distance of about 200,000 kilometers, it weighs about 30 tons total. That's with using Xylem and Dyneema. And you'll see here an equatorial base, so that the tether attached to the moon would be attached to the lunar equator at the 0 longitude point, and that happens to be a location on the moon called Sinus Medii. So I've been looking to see what's interesting around Sinus Medii, because that's probably where we put our first mining base. Here's another picture. And you see on the left, it says released cargo goes to HEO, that's high Earth orbit. So you can pull material from the moon and transfer it along the tether using little robot climbing machines. And then once you get past the L1 point, the tether is actually fairly deep in Earth's gravity well, and you release an object from there, and it'll fall down towards the Earth. It won't drop like a stone because it's still got some tangential velocity, but it'll go into an elliptical orbit, and then it'll enter the Earth's atmosphere. So here's a copy of the report by, what is the front page of the report by Jerome Pearson. Well, this is what he did in 2005. Yeah, Jerome Pearson wrote some notes, and he published some papers in 1979. In 2005, he actually got a NASA contract to look at it in a little bit of detail. So this is an idea that's workable. We can do it with today's technology. We don't need any new breakthrough materials. We don't need any warp drives. It can be done. A lot of people just don't believe it can be done, but it's all in this report. Now, there's another group that figured out that it could be done independently over in Israel at I forget the name of the university, but they call it Jacob's Ladder. And I found out about them about 2 years ago. They published their reports in 2010. The advisor of their program, Dr. Alexander Kogan, is a very interesting man, actually. I've spoken to him. That's where, yeah, it's at Technion, that's right, Technikon, Israeli Institute of Technology. Alexander Kogan was one of the leading scientists in the Soviet space program. And at the end of the Cold War, he emigrated from Russia to Israel, where he became a professor at Technion University. But he calculated the trajectories for most of the Soviet lunar probes and their probes to Venus and Mars. So he's one of the world's experts in orbital mechanics. Recently he retired, and he now lives in Canada. But they did a very nice detailed study, and they published that. And they've actually got an 84-page report. And the numbers they come up with are entirely consistent with Pearson's numbers. So every team that's taken a serious look at the lunar elevator has come up with about the same conclusions, that we have materials that can do it and that it can work. We've been trying to get NASA interested in it, but so far they haven't spent any more money on it. Since that 2005 contract, they haven't spent any more study money on it. Part of it seems to be political. The current administration, the Obama administration, has an explicit policy not to send humans back to the moon. And they've been focusing on going to Mars. So that the moon is a dirty word in NASA these days. If you tell them, I've got a project to go to the moon, it just gets spiked. They don't want to hear about it. They just want to hear about Mars because that's what the White House wants. So we're kind of stuck at the moment until that thinking changes. You might have heard about there are some private companies, one up in Seattle called Planetary Resources, and another one called Deep Space Industries, and there are a couple of others that talk about mining asteroids. I'm all in favor of that, and the advantage of going after near-Earth asteroids is they're so much smaller than the moon, so you don't need a big rocket to land on them. But the thing they don't talk about very much is that the round-trip travel time to even the closest asteroid is about 5 years. Some of them it takes 10 years. Even the ones that swing by the Earth, they actually swing by so fast that, and they only pass by the Earth about once every several years. So you have to, if you want to grab it, you have to chase after the asteroid, rendezvous with it, grab onto it, and then you got to wait another 5 years until it comes back to the Earth when you can actually bring it in. Whereas the round trip time to the moon is about 7 days. So, from a commercial and logistic standpoint, it's a lot easier. And with the lunar elevator essentially gets rid of the advantage that asteroids have because it removes the problem of the energy for soft landing on the moon. So that's essentially it. I think we're about reached time. I'm happy to answer questions. I encourage you all to consider joining the L5 Society if you'd like to see these kinds of ideas come to fruition. We're working on it, and we'd be happy to collaborate.
So there's some questions.
All right, how much time do we have?
Oh, yeah, we're fine.
Okay, yeah, so go ahead, let me grab my glass of water. Thanks. Yes, sir, shoot.
So when the mined material reaches high Earth orbit, how is it then, what's the vision for collecting it and then bringing it down to the surface?
Right. It should be fairly simple. It would use ballistic reentry capsules. So we'd have to initially build these reentry capsules on Earth and then shoot them up to the L1 point, and then buckets of material coming up to the moon would have to be enclosed in these reentry capsules, and then the reentry capsule would drop down to Earth. And in principle, they could be fairly simple. I've had correspondence with some people saying, well, you got to have these hypersonic heat shields and guidance system and attitude control, and well, not really. And actually, the only reason we have those is if you're carrying people, astronauts, then you want to keep the deceleration down to about 7 or 8 G's tops, because you want to have the humans survive the passage. And that makes it challenging. If you want to keep the controlled deceleration down to that level, then you have to do some fairly sophisticated maneuvering in and out of the atmosphere to bring it down, and that makes it a little expensive. But for rocks, we don't have to do that. And the Soviets, and it becomes a lot simpler. And by comparison, the Soviet unmanned sample collection, the first one was Lunar 16 in April 1970, and then they had a couple of others, Lunar 20 and Lunar 24. Even quite recently, I've read some detailed reports of how those things actually worked, and they were incredibly simple. They just had a rocket sitting there, so they soft landed the probe onto the moon, and it had a rocket on it, and it had a sample with a drill, and it drilled in, collected the sample, and the arm came up, and it inserted the sample into this spherical ball at the top, and then the door closed, and then they waited till the Earth rotated so that the target location of the Soviet Union was in the right point, and then they fired this rocket at exactly the right moment, so it would take off and go into a direct free fall trajectory, and at that point it was a dumb bullet, and there there were no mid-course corrections, so they had to get it right first time, and they did 3 times. They got it exactly right 3 times, and the entry capsule was a ball, just a sphere about that much across, and it had no attitude control system, no propulsion, no communications. It was a dead dumb bullet, and it fell for 3 days, and then it hit the atmosphere, and it was a ball, and it had an offset center of gravity in it, so that it would oriented itself to a specific angle as it entered the atmosphere. And then it had a little G switch which detected the G load and popped and fired the explosive bolt to let the parachute out and turn on a beacon. And that was it. And it was dead until the point at which the parachute came out and the radio beacon came on. And then they sent helicopters to go looking for it and pick it up. And they didn't. I mean, got all 3 of them. And it was cheap and simple. No, no sophisticated skipping in and out of the atmosphere or anything. It just slammed straight in.
I see these coal trains coming by Vancouver, and I sort of imagine a coal train type, series of coal cars. Yeah, absolutely.
Up and down the lunar elevator. There are some practical logistical challenges. I mean, we want to maximize the throughput. So, and Kogan's team calculated that it takes about 5 or 6 days to travel from the L1 point to the lunar surface with a sort of electric elevator car going down it. If you try to go any faster than that, it starts to put quite a high strain on the tether, and it wouldn't be able to cope with it. So to stay within the structural strength margins, you have to keep the speed down about, I think it was at 100 meters per second or something like that. And there's a couple of ways of doing it. I've been playing around with some ideas. I mean, you could, when you're coming from the surface up to the L1, you could accelerate, and then you have to cruise up, and then you have to decelerate and come to a dead stop at the L1, unload the cargo, put it into an entry capsule, and then reverse the process, and then accelerate the entry capsule towards the Earth. But that doesn't maximize your throughput. So I've been coming up trying to think about, well, could you have the thing collide at 100 meters per second? So or you'd have to have your entry capsule start accelerating towards the Earth so that the other thing catches up with it, then transfers the payload while they're moving at 100 meters per second. Then the carrier hits the brakes and slows down while the other thing keeps going. But then the carrier, without having so much mass, you could probably break it quite hard without putting a big strain on the cable. And then it can go back, so you might get a higher throughput that way. So it's fun thinking about stuff like that. I'd like to get some computer animations to show that. Yes, go ahead.
Would the operation be fully automated, or would you need some kind of engineering crew there?
Initially, it would be completely automated. That's the idea, to keep the cost down. There are some advantages to having human operators at the L1 point, because the round trip delay of the radio signals between the Earth and the Moon is about 3 seconds. But from the L1 location to the lunar surface, the round trip is about 0.1 second. And some interesting experiments have been done on performance of human operators with those kind of time lags. And with a 3-second time lag, it's almost impossible to do anything. You just get completely confused. But with a 0.1 second delay, you can operate effectively. When the Soviets operated 2 lunar rovers on the Moon, Lunar 1 and Lunar 2, and they were remotely operated by operators sitting on the Earth. And they had to have a heck of a lot of training for them to be able to do that. And there's a very interesting TV documentary called The Tank on the Moon, which was on PBS a few years ago, which showed how they trained these guys to actually do that. But it takes a special type of person with a exercise that has been done is try to tie your shoelaces with a 3-second delay. So you're looking through a camera and you're seeing the shoelaces as they were 3 seconds ago and you're trying to tie it. And it typically takes people 20 to 30 minutes to tie their shoelaces with a 3-second delay. With a 0.1-second delay, you can do it like in a minute, that kind of thing. And so we'll probably have humans at the L1 location fairly early in the process to control operations on the lunar surface. And then we'll probably have humans on the lunar surface at some point as well. But I envision it to be mostly automated, and humans would be there to repair the machines when they go wrong. Yeah, go ahead.
For gravitational reasons, it would be much more valuable to have a space elevator on Earth. You know, the Arthur Clarke
Sure. Yeah.
design.
Right. Thank you for bringing that up. Yeah.
So
I didn't
what
know that.
is the efficiency? What is the efficiency of needing an elevator on the moon, where it's many, many times more valuable to be able to change the weight differential?
That's true. It would be. There's only one problem, is that we do not have materials today from which you could make on Earth an elevator from the Earth to space. It's a theoretical concept only. There is a class of materials that exists called carbon nanotubes, and where theoretically, if you could make strands of carbon nanotubes long enough, we could build an elevator from the surface of the Earth through the geosynchronous orbit. And it would be wonderful if we could ever get that done, but nobody knows if and when we'll have materials strong enough to do that. So for now, it's just a theoretical concept. And there are groups of people that continue to study the Earth space elevator. There's a group that has an annual conference every year in Seattle called the ISEC, International Space Elevator Consortium, and I know those guys quite well, and I sometimes hang out with them and we kick around these ideas. But I'm excited by the lunar elevator because we can do that right now. I have materials in my apartment at home which are perfectly adequate, for a free sample that the company sent me. In terms of the cost, I think I showed a baseline. We have what we've designed, a minimalist lunar elevator, which could be done at a cost of $800 million, which is pretty cheap. Most of that, the cost of the tether itself is about $20 million. It's actually a very small part of the overall system cost. And not only are these tether materials available and workable, they're actually quite cheap. And the main cost of the lunar elevator would be the cost of the control system and the hardware to deploy and operate the lunar elevator. So my colleagues who are working on the Earth space elevator, some of them, kind of scoff at the lunar elevator and say, well, what's the point? I mean, you don't get anything like the value you would get with an Earth elevator. And it's true, you don't, but the difference is that they can't tell me when they'll be able to build an Earth elevator. I can tell you that I can build this in 5 years, and I can do it with a firm fixed price contract. If you got the money, I'll sign on the dotted line and I'll get it done. You can't do that with the Earth space elevator. Yes, ma'am.
To build a moon space elevator, you first have to have some kind of a big assembly.
Actually, not
on the moon.
No, you don't.
And we haven't been there for 30 years.
No, you don't need anything on the moon. This entire thing can be built as a 30-ton package on the Earth, and a 30-ton package can be launched to L1 on a single rocket, such as an Atlas V or a Delta. So it's all built in a package on a factory in the Earth. You can build it in that hangar and truck it out to Kennedy, put it on an Atlas, and it'll shoot up from Earth to the L1. And then the tether is deployed from there. It's deployed simultaneously downwards towards the moon and then upwards away to the counterweight. And then it'll go, and then the tether portion, when it reaches the moon, will use what we call lawn dart penetrators that will fire and capture into the lunar surface. So it can actually be done without any infrastructure on the moon at all. It's not that difficult. Yes, ma'am. Go ahead.
Maybe way too early to ask this question.
Sure.
It has to do with policing and greed. I mean, if there's money to be made, what, you know, I mean, and you're saying it's that doable. I mean, who gets, you know, is it going to be a race to who gets what, or is there anything now, grassroots, with all these organizations that, you know, the international?
Yeah, that's an interesting question. The legal framework by which it would be done.
Who owns the moon? I guess.
It depends who you're talking to. Most people look to the United Nations, and there's two United Nations treaties. There's the 1967 Outer Space Treaty, which most countries in the world have signed on to, including the United States, all the great powers. Everybody from the UN Security Council has signed on to the 1967 treaty. And that treaty has a couple of provisions in it. And it's modeled a lot on the Law of the Sea Treaty. Every nation is allowed to travel through space in the same way as they're allowed to travel on the high seas. So any spacecraft launched from any nation is the responsibility of that nation. And that includes a little liability clause in the treaty where if you launch a satellite and it crashes on another country, the country that launched it has to pay for the cleanup, for example. Plus, there are things like countries are not allowed to interfere with each other's spacecraft. So if, you know, Russia launches a spacecraft, America can't go there and mess around with it. It's not without their permission. And there's recognitions of exclusion zones around spacecraft. The UN treaty is kind of vague on commercial property rights. One of the key provisions is no nation is allowed to appropriate or declare sovereignty over the moon or any other celestial body. So the United States cannot make the moon the 51st state of the United States. That's illegal under international law, and it's also illegal under U.S. law because the U.S. has ratified the 1967 treaty. However, it counts like the high seas, so anybody you can get in a boat and sail Tahiti if you want to, and you can get on a spaceship and fly to the moon if you want to. And you can, legal scholars argue over there's a lot the UN Moon Treaty does not say. Most legal scholars say that you can mine the moon commercially, provided you're not interfering with anybody else who's there. And basically, as long as you don't interfere with anybody else. And you cannot claim that you own the moon as such, but you can pull material off the moon, and you can establish a base on the moon, and you can establish a safety zone around your base so that third parties are not allowed to enter your perimeter. That's illegal. There was another treaty, a draft treaty that came out in 1979 that they called the Moon Treaty, which is a little more strict. And that